There is a particular kind of moment in the history of science, not dramatic, not announced with ceremony, when a measurement returns a value that simply does not fit, not approximately fit, not fit within some acceptable margin of error, simply does not fit. The instruments are checked, the calculations are reviewed, the data is reanalyzed by independent teams in independent laboratories, and the number persists, patient, immovable, quietly insisting that something, somewhere in the elegant architecture of our best understanding of the universe, is either incomplete or wrong. These moments are rare. They are also, in the long view of scientific history, among the most valuable things that careful measurement can produce, because every time the map disagrees with the territory, every time the model and the observation refuse to reconcile, something real is being revealed, not a failure of science, a success, the success of instruments sensitive enough to detect the place where our understanding ends and something deeper begins. Tonight, we journey to that place. The James Webb Space Telescope, the most powerful observatory humanity has ever deployed, has been accumulating observations since early 2022, and among the results it has produced, one pattern has emerged with increasing clarity and increasing statistical weight, a pattern that deepens what was already the most significant unresolved tension in modern cosmology, a pattern that has prompted careful, measured, scientifically honest statements from researchers that our models of the universe, models built on the foundations laid by Einstein, refined across a century of observation, may be missing something fundamental. This is not a story of catastrophe. The universe has not changed. The laws of physics are not broken. But our description of those laws, our map of how the cosmos works, may be drawing lines that do not quite match what the territory actually contains. If you love exploring the cosmos, a like and subscribe would mean the world to us. Let's begin. To understand what James Webb has found, and why it matters, we must first understand the framework that the observations are testing. The theoretical architecture of modern cosmology. The models that, for a century, have described the universe with extraordinary precision and have been confirmed by observation after observation. That framework rests, at its foundation, on Albert Einstein's general theory of relativity, published in 1915. General relativity replaced Newton's conception of gravity as a force acting at a distance with a more profound description. Gravity is the curvature of space-time caused by the presence of mass and energy. Matter tells space-time how to curve. Curved space-time tells matter how to move. This is not merely an abstract restatement of Newton. General relativity makes predictions that differ from Newton's gravity in specific, measurable ways, and every one of those predictions has been confirmed experimentally. The bending of light around massive objects, the slowing of time in strong gravitational fields, the precession of Mercury's orbit, the existence of gravitational waves, ripples in space-time produced by accelerating masses, detected directly for the first time in 2015 by the LIGO Observatory. General relativity is one of the most thoroughly tested theories in the history of physics. It has passed every experimental test ever devised for it. Applied to the universe as a whole, to the cosmos at its largest scales, general relativity predicts that the universe should be dynamic, not static. It should be either expanding or contracting. Einstein himself, initially uncomfortable with this implication, introduced a term into his equations, the cosmological constant, to force a static solution. He later called this his greatest blunder when Edwin Hubble's observations confirmed that the universe is indeed expanding. From the expanding universe, cosmologists worked backward in time and arrived at the Big Bang, the moment approximately 13.8 billion years ago, when everything we can observe emerged from an extraordinarily hot, dense state. The universe has been expanding and cooling ever since. This picture, general relativity applied to an expanding universe originating in a Big Bang, is the foundation, and it has been spectacularly successful. Built on the foundation of general relativity, modern cosmology has developed what is called the lambda CDM model, sometimes described as the standard model of cosmology. It is the framework within which essentially all professional cosmological research operates, against which all observations are compared, and from which predictions about the universe's past, present and future are derived. Lambda refers to the cosmological constant, the term Einstein introduced and later abandoned, which has been reintroduced into modern cosmology to describe what is now called dark energy. Dark energy is a form of energy inherent to space itself, distributed uniformly throughout the universe, not associated with any particle or object, and responsible for the accelerating expansion of the universe that was discovered in 1998. CDM stands for cold dark matter, the dominant form of matter in the universe by mass, approximately 5 times more abundant than ordinary atomic matter. Dark matter does not interact with light in any way we have detected. It is invisible, but its gravitational effects are unmistakable. Galaxies rotate in ways that only make sense if surrounded by enormous halos of invisible mass. Galaxy clusters bend the light of objects behind them, gravitational lensing, in ways that require far more mass than their visible stars and gas contain. The large-scale structure of the universe, the cosmic web of filaments and voids, formed in ways consistent with the presence of dark matter, acting as the gravitational scaffold around which ordinary matter accreted. Together, dark energy and dark matter constitute approximately 95% of the universe's total energy content. Ordinary matter, everything made of atoms, everything we can see and touch and build instruments from, is only about 5%. This is the universe as we currently understand it, mostly invisible, mostly unknown in its fundamental nature, described with extraordinary mathematical precision in its behavior, mysterious in its constitution, and it is this framework, lambda CDM, that Webb's observations are probing, testing, and in specific ways, finding incomplete. At the heart of tonight's exploration is a single number, a number that describes one of the most fundamental properties of the universe, the rate at which space itself is expanding. It is called the Hubble Constant, named for Edwin Hubble, who first measured cosmic expansion in the 1920s. The Hubble Constant, usually denoted h0, tells us how fast galaxies are moving away from us as a function of their distance. More specifically, it tells us how many kilometers per second a galaxy recedes for every megaparsec of distance from us. A megaparsec is approximately 3.3 million light-years. The value of the Hubble constant matters enormously. It determines the age of the universe, the time elapsed since the Big Bang. It determines the scale of the observable universe. It determines how the universe will evolve in the future. It is, in a real sense, one of the most fundamental quantities that describes the cosmos we live in. For decades, measuring the Hubble constant precisely was one of the central goals of observational cosmology. Early measurements disagreed by factors of 2, a situation that persisted until the Hubble Space Telescope was launched and began systematically measuring cosmic distances with unprecedented precision. Eventually a consensus value emerged, and then, as measurements became more precise, something unexpected happened. 2 very different methods of measuring the Hubble constant, measuring it from the early universe on one hand and measuring it from the local universe on the other, began to return values that disagreed with each other. Not by much in absolute terms, but by an amount that, as the measurements became more precise, became statistically very significant. This disagreement has a name. It is called the Hubble tension. And it is, as of the time of writing, one of the most important unresolved problems in cosmology. James Webb has entered this conversation, and the data it has produced has not resolved the tension. It has deepened it. There are 2 fundamentally different ways to measure the Hubble constant, 2 independent methods that, in a consistent universe, should produce the same answer. Understanding why they disagree requires understanding both methods in some depth. The first method looks backward, all the way to the universe's infancy. Approximately 380,000 years after the Big Bang, the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms for the first time. Before this moment, the universe was an opaque plasma, a hot, dense fog through which light could not travel freely. When the hydrogen formed, the fog cleared. Light that had been trapped in the plasma streamed outward in all directions. That ancient light, now stretched by the universe's expansion to microwave wavelengths, still pervades all of space today. It is called the Cosmic Microwave Background, or CMB. It was first detected in 1965, and its detailed mapping by satellites including COBE, WMAP, and most recently the Planck satellite has provided an extraordinarily precise picture of the early universe. The CMB contains a wealth of information about the physical conditions at the moment of its release. The tiny temperature fluctuations in the CMB, variations of only about 1 part in 100,000, encode the density variations of the early universe that would later grow, under gravity, into galaxies and galaxy clusters. From these fluctuations, cosmologists can extract the values of all the parameters of the lambda CDM model, including the Hubble Constant. The value obtained from Planck satellite CMB measurements is approximately 67.4 km per second per megaparsec. This is a measurement of the Hubble constant as it was implied by the early universe, extrapolated to the present day using the lambda CDM model. It is precise to better than 1%, and it disagrees with the other measurement method. The second method of measuring the Hubble constant works from the present, from the nearby universe, using the direct observation of astronomical objects at known distances. It is called the cosmic distance ladder, and it is one of the most carefully constructed measurement frameworks in all of observational astronomy. The distance ladder works by building up from nearby, well-calibrated distance measurements to progressively more distant ones. Each rung of the ladder uses a different type of object or phenomenon, calibrated against the rungs below it. The first rung uses geometric methods, parallax measurements of nearby stars, where the star's apparent position shifts slightly as Earth orbits the Sun, allowing its distance to be calculated through simple trigonometry. This is as direct a measurement as astronomy can make. The second rung uses Cepheid variable stars, a class of pulsating giant stars whose luminosity, intrinsic brightness, varies in a precise regular cycle. The period of the cycle is directly related to the star's intrinsic luminosity, a relationship discovered by astronomer Henrietta Swan-Leavitt in 1912. By measuring the period of a Cepheid's pulsation, you can infer its true brightness. Comparing this to its apparent brightness gives its distance. The third rung extends further using Type 1a supernovae, exploding white dwarf stars that, at their peak, all achieve approximately the same intrinsic luminosity. These cosmic explosions are brilliant enough to be observed across billions of light years and serve as standard candles, objects of a known brightness, for measuring distances across the universe. By combining these rungs, parallax to Cepheids to supernovae, astronomers can measure distances to galaxies across large portions of the observable universe and determine how fast those galaxies are receding. The value of the Hubble constant from this method, measured most precisely by the SH0ES team using Hubble Space Telescope data, and subsequently refined with Webb, is approximately 73 km per second per megaparsec, 67 versus 73, a difference of approximately 8%. In the cosmos, 8% is a small number. In the precision measurement of a fundamental constant, it is enormous. For years, the Hubble tension, the discrepancy between the CMB-derived value and the distance ladder value, was a source of professional unease in cosmology. Experts debated whether it was real or whether it arose from systematic errors in one or both measurement methods. Systematic errors, hidden biases in how measurements are made, calibrated, and interpreted, are the natural first suspect when two measurements disagree. Perhaps the Cepheid calibration was slightly off. Perhaps the Type 1a supernovae were not quite as standard as assumed. Perhaps the CMB analysis contained some subtle modelling assumption that introduced a bias. To test these possibilities, astronomers turned to alternative measurement methods, independent rungs that did not rely on Cepheids or supernovae. Red giant branch stars, a class of stars whose peak luminosity is well determined by stellar physics, were used as distance indicators in place of Cepheids. Gravitational wave events from merging neutron stars, which provide an entirely independent distance measurement through the amplitude of the gravitational wave signal, were used as yet another standard siren. Each new method produced a result, and the pattern was consistent. Methods that measured the local universe tended to produce higher values of the Hubble constant, clustered around 70 to 73. Methods that inferred the constant from the early universe tended to produce lower values, clustered around 67 to 68. By the early 2020s, the statistical significance of the discrepancy had grown to what is called 5 sigma, meaning the probability of the disagreement arising by chance in a perfectly consistent universe with no systematic errors was less than 1 in 3.5 million. In physics, 5 sigma is the conventional threshold for claiming a discovery. It is also the conventional threshold for saying, this is real. The Hubble tension, by this point, was real, and then Webb began its observations. When James Webb was turned toward the cosmic distance ladder, toward the Cepheid variable stars and the galaxies containing them that form the crucial rungs of the measurement framework, the expectation in some quarters was hopeful. Perhaps Webb's extraordinary sensitivity and resolution would reveal systematic errors in the Hubble Space Telescope measurements that had previously been impossible to detect. Perhaps the Cepheid measurements would shift when examined with better instruments. The results of Webb's Cepheid measurements, analysed by the SH0ES team and published beginning in 2023, were unambiguous in their implications, and not in the direction some had hoped. Webb's measurements of Cepheid variable stars in nearby galaxies confirmed the Hubble Space Telescope measurements. The distances to these galaxies, measured with Webb's superior infrared sensitivity and resolution, which allows individual Cepheids to be cleanly resolved even in crowded galactic environments, where Hubble measurements might have been contaminated by overlapping starlight, were consistent with the distances Hubble had measured. The Cepheid calibration was not the problem. The distances were not wrong. The local measurement of the Hubble constant, approximately 73 km per second per megaparsec, was not a systematic artifact of imprecise Cepheid measurements. Webb had essentially ruled out the most straightforward systematic explanation for the Hubble tension. The distance ladder was solid. The tension was not going away. In the words of Adam Rees, one of the Nobel laureates who discovered the accelerating expansion of the universe and a leader of the SH0ES team, Webb had made it clear that the Hubble tension is not due to a systematic error in the Cepheid measurements. The problem, whatever it is, lies elsewhere. That elsewhere, the space of possible explanations that remain after the systematic error hypothesis has been largely ruled out, is where the most interesting science is now happening. Beyond its role in refining the distance ladder, Webb has contributed a second and equally significant dimension to the cosmological tension through its observations of the early universe, the first galaxies, forming in the first hundreds of millions of years after the Big Bang. These observations began generating discussion almost immediately after Webb's first deep field images were released in mid-2022. The images were extraordinary in their depth and clarity, and among the objects they revealed were galaxies, candidate galaxies, requiring spectroscopic confirmation that appeared to be unexpectedly large, unexpectedly massive, and unexpectedly structured for objects existing so early in cosmic history. The lambda-CDM model makes specific predictions about galaxy formation in the early universe. In the standard picture, the first galaxies should be small, irregular, and relatively low in stellar mass. They should build up gradually through mergers and accretion, over hundreds of millions to billions of years. The most massive, most structured galaxies should appear later, after sufficient time for the hierarchical growth process to operate. Webb's early observations found objects that challenged this picture. Galaxy candidates at redshifts corresponding to the universe being only a few 100 million years old, sometimes called cosmic dawn, that appeared to contain stellar masses comparable to or exceeding the Milky Way. Objects so massive, so early, that forming them would require the conversion of gas into stars at rates approaching the theoretical maximum, and would strain the predictions of the standard model. The early analysis was subject to important caveats. Photometric redshifts, distance estimates based on the colours of objects rather than their spectra, can be wrong. Spectroscopic confirmation is required, and some of the most extreme early candidates have, upon spectroscopic follow-up, proven to be at lower redshifts than initially estimated, or to be quasars rather than galaxies, reducing their implied stellar masses. But even accounting for these revisions, The statistical picture that emerges from Webb's first years of deep field observations is one of a universe that built its large structures earlier, faster than our standard model predicted. Let us pause for a moment and consider what we now have. Not any single observation, but the pattern of observations that has accumulated across Webb's first years of operation. The Hubble tension, the discrepancy between the early universe and local measurements of cosmic expansion, has been confirmed and strengthened. The systematic error explanation has been largely ruled out. The tension is real, at a statistical significance that exceeds any conventional threshold for requiring explanation. The early galaxy problem, the presence of galaxies in the first few 100 million years of cosmic history that are larger and more massive than the standard model comfortably accommodates, has been documented across multiple deep field surveys and multiple independent analysis teams. The problem has not disappeared under scrutiny. It has persisted, and in some analyses strengthened, as more data has accumulated and spectroscopic confirmations have proceeded. Additionally, ongoing analyses of the large-scale structure of the universe, the distribution of galaxies across billions of light-years, traced by enormous surveys, have in some cases found tensions with lambda CDM predictions. The clustering of matter on certain scales appears, in some analyses, to be different from what the standard model predicts given its CMB-derived parameters. Individually, any one of these tensions might be attributed to unidentified systematic errors, to statistical fluctuations, to incomplete theoretical modelling. Taken together, as multiple independent observations from multiple independent methods, all pointing in the same direction of our model may be missing something. They carry a collective weight that the cosmological community is taking seriously. No single measurement has shattered Einstein. That is not how science works, with a single dramatic break. What is happening is subtler, more patient, and in its own way more significant. The map is being found in multiple places simultaneously to disagree with the territory. When the delta refuses to yield to systematic error explanations, when the measurements are confirmed as reliable and the tension remains, the next step is theoretical. What new physics might resolve the discrepancy? What addition to or modification of the standard model could bring the early universe and local measurements into agreement? One of the most carefully developed proposals is called early dark energy. It proposes that in addition to the late universe dark energy that drives the current accelerating expansion, there was a brief episode of additional dark energy in the early universe, specifically in the period just before the cosmic microwave background was released. In the standard lambda CDM model, the pre-CMB universe is dominated by radiation and matter, with dark energy playing no significant role. Early dark energy models add a component that behaves like dark energy, providing additional expansion during this early epoch, then fades away and becomes negligible after the CMB is released. The effect of this early burst of additional expansion is to change the acoustic scale, a characteristic length that is imprinted in the CMB's temperature fluctuations and that serves as a kind of cosmic ruler. By slightly modifying this scale, early dark energy models can shift the CMB-derived value of the Hubble constant upward toward the locally measured value. The challenge is that early dark energy models must be carefully tuned to shift the Hubble constant without worsening the agreement between the CMB and other observations. The large-scale structure of the universe, the clustering of galaxies, the abundance of galaxy clusters. The CMB fits the standard model so well across so many different observables that any modification must be made with extraordinary care. Several early dark energy models have been proposed and tested against available data. Their fit to the Hubble tension is promising, but they tend to create tensions elsewhere, worsening the fit to some aspects of large-scale structure, for example. No version has yet been found that resolves the Hubble tension cleanly without introducing new discrepancies. The search continues. Another class of proposals goes deeper, not modifying the content of the universe, as early dark energy does, but modifying the theory of gravity itself. General relativity has been tested with extraordinary precision in the solar system, in gravitational wave observations, and in many other regimes. But cosmological scales, the behavior of gravity across billions of light-years, are less well tested. Perhaps general relativity, as precise as it is in its tested domains, requires modification at cosmological scales. Various theories of modified gravity have been proposed over the decades. Some modify the relationship between mass and gravitational force at very low accelerations. Modified Newtonian dynamics, or MOND, was originally proposed to explain galaxy rotation curves without dark matter, though it struggles to explain the full range of cosmological observations. Others modify the field equations of general relativity by adding terms that become significant only on very large scales. More recently, proposals have emerged from a different direction, from attempts to unify general relativity with quantum mechanics. String theory, loop quantum gravity, and related frameworks all make predictions that differ from standard general relativity in specific regimes. Some of these predictions, applied to cosmology, could produce differences in the expansion history of the universe that might be relevant to the Hubble tension. It is important to be honest about where these alternatives stand. None has yet been demonstrated to resolve the Hubble tension while preserving the extraordinary range of cosmological observations that lambda CDM successfully explains. None has clear, unambiguous observational support beyond the tensions it is proposed to explain. They are live possibilities, explored by serious physicists, but not yet established alternatives. What they represent is the range of conceptual space within which a resolution might be found. The territory beyond the current map is large. The number of possible maps that might fit the territory better than the current one is, in principle, enormous. Finding the right one requires more data, more analysis, and the patient work of theoretical elimination. There is a class of proposed explanation for certain cosmological observations, including, in some versions, aspects of the Hubble tension, that ventures beyond the conventional framework of physical theory into more speculative territory. It involves the concept of the multiverse. In various forms, the multiverse arises naturally from certain theoretical frameworks. Inflationary cosmology, the theory that the early universe underwent a brief period of extraordinarily rapid exponential expansion, predicts, in its most common versions, that inflation may be ongoing in most of space, with our observable universe being one of many bubble universes that formed when inflation locally ceased. Each bubble universe may have different physical parameters, different values of the cosmological constant, different particle masses, different effective laws of physics. If we live in one bubble among many, the values of the cosmological constant and other parameters in our universe might be understood not as fundamental constants, to be derived from deeper theory, but as selection effects. We observe the values we do because these values permit the existence of galaxies, stars, planets, and observers. In this framework, a universe with a cosmological constant very similar to what we observe, the small but non-zero dark energy we measure, might be expected as a consequence of the selection effect that only such universes produce observers who can measure it. The relevance to the Hubble tension is indirect and speculative. If the values of cosmological parameters are not fixed by any single unique theory, but are drawn from a distribution across bubble universes, then the apparent tensions in our measurements might reflect the particular values our universe happens to have, values that do not perfectly satisfy any simple, elegant theoretical relationship. This is genuinely speculative. The multiverse is not directly testable in any conventional scientific sense. It cannot predict specific observations that would distinguish it from alternatives. Its value as a scientific hypothesis is debated. But it is worth noting as the frontier of what contemporary physics allows itself to contemplate, the edge of the map where, beyond the carefully drawn lines of testable theory, the territory of pure speculation begins. The title of tonight's documentary makes a bold claim, that every model since Einstein has been shattered. Let us address this directly and honestly, because scientific accuracy matters more than dramatic framing. Einstein's general theory of relativity has not been shattered. It has not been disproven. It remains one of the most precisely tested theories in the history of science, confirmed by an extraordinary range of observations across more than a century. The bending of light, the detection of gravitational waves, the behavior of pulsars, the existence of black holes, all are precisely described by general relativity. What the Hubble tension and related cosmological anomalies suggest is not that general relativity is wrong, but that the specific application of general relativity to the universe as a whole embodied in the lambda CDM standard model, may be incomplete. The model may be missing a component. It may have a parameter that needs adjustment. It may require an extension, additional physics that operates in regimes or epochs that the model currently handles incorrectly. This distinction is important. Newton's theory of gravity was not wrong. It was incomplete. It worked extraordinarily well for most applications: planetary motion, falling bodies, tides. Einstein's general relativity was not a rejection of Newton, but an extension. It recovered Newton's results in the appropriate limits while also correctly describing phenomena that Newton's theory could not, such as the precession of Mercury's orbit and the bending of light. The extension of lambda CDM that the Hubble tension requires, whatever it turns out to be, will similarly be an extension rather than a rejection. The extraordinary success of the standard model in describing the vast majority of cosmological observations will be preserved. But whatever new physics is needed to resolve the tension will add something, a new component, a modification, a deeper understanding that makes the description more complete. This is not the shattering of Einstein. It is the continuation of the scientific tradition that Einstein himself embodied, the patient, rigorous, mathematically precise extension of our understanding of the universe. James Webb's contribution to the cosmological tension is not finished. It has, in its first years of operation, confirmed that the Hubble tension is not a systematic artifact of Cepheid measurements. It has documented the early galaxy problem with unprecedented clarity, and it continues to gather data that will constrain the range of possible explanations. Among Webb's ongoing scientific programs are observations designed to further refine the distance ladder, using multiple distance indicators, not just Cepheids, to build a more redundant and cross-checked measurement of the local Hubble constant. The goal is to reduce the remaining measurement uncertainty to the point where, if any residual systematic error exists, it would be detectable. Webb is also characterizing the atmospheres and properties of early galaxies in greater detail, building the spectroscopic sample that allows the statistical analysis of the early galaxy population to be put on a firmer footing. As more galaxies at high redshift are confirmed spectroscopically, and their properties measured, the statistical comparison with model predictions will become more powerful. The Dark Energy Spectroscopic Instrument, DESI, a ground-based survey that has been mapping the three-dimensional distribution of galaxies across a large volume of the universe, released results in 2024 suggesting that dark energy may not be constant, that it may have varied over cosmic time. If confirmed, this would represent a departure from the simplest form of lambda CDM and could have implications for the Hubble tension. Webb's observations provide complementary information about the universe's expansion history that can be compared with DESI's findings. The Euclid Space Telescope, launched in 2023, is conducting a wide-area survey of galaxy shapes and clustering that will probe the growth of cosmic structure with unprecedented precision. Its results will further constrain the range of viable cosmological models. All of these instruments are collectively applying increasing pressure to the standard model, testing it from multiple directions simultaneously, building a comprehensive picture of what it can and cannot accommodate. There is something worth sitting with quietly in the situation we find ourselves in, cosmologically speaking. We have built, over the past century, a model of the universe of extraordinary power and precision, a model that correctly describes the abundance of light elements formed in the first minutes after the Big Bang, that correctly predicts the temperature fluctuations in the cosmic microwave background, that accurately describes the large-scale distribution of galaxies across billions of light-years. And this model, this extraordinary achievement of human intellect and careful observation, is now disagreeing with itself. The part of the model that describes the early universe and the part that describes the local universe are returning inconsistent values for one of the most fundamental quantities in cosmology. What does it mean when our best model breaks down? It means, first and most simply, that nature is richer than the model, that the territory contains something the map does not show. This has been true at every stage of scientific history. Newton's model was the best model of its era and did not contain the warping of space-time. Maxwell's model of electromagnetism was the best model of its era and did not contain quantum mechanics. Each successive model was not wrong, but incomplete, a valid description of the territory within certain limits, a map that ran out before the territory did. The Hubble tension may be telling us that our current best model, lambda CDM, has reached the boundary of its validity, that beyond this boundary there is new territory, new physics, a deeper description of the universe that contains lambda CDM as a limiting case, the way general relativity contains Newtonian gravity, but that sees further. What that deeper description contains, whether it involves new forms of dark energy, modifications to gravity, new particles from the early universe, or something not yet conceived, is genuinely unknown. The answer lies somewhere in the data being gathered now, and in the theoretical work being done now, and in the insights that have not yet arrived. We are at an edge. Edges are the most interesting places to be. Throughout the history of astronomy, from the first careful observations of planetary motion to the detection of gravitational waves, the universe has been a patient and ultimately generous teacher. It has allowed us to build models that work beautifully within certain regimes, and then, when our instruments became sensitive enough to probe the edges of those regimes, it has shown us that the model needed to grow. This is not a source of frustration. It is a source of profound reassurance about the nature of scientific inquiry. The universe is consistent. It operates by laws. Those laws are discoverable, not all at once, not easily, not without patient, careful, rigorous work, but discoverable. The history of science is the history of that discovery, proceeding across centuries and generations, each one building on the last. The Hubble tension is the universe showing us through the precision instruments of our era, where the current chapter of that discovery ends, where the next chapter must begin. It is not a message of failure. It is an invitation. The generation of cosmologists and physicists who will extend lambda CDM, who will identify whatever new physics resolves the Hubble tension and accommodates Webb's early galaxy observations, are working now. Some are students. Some are early career researchers examining the latest DESI results, or planning the next Webb observation program. Some of them do not yet know that they will be the ones to find the answer. The universe has been waiting approximately 13.8 billion years for minds to develop that could ask these questions. It seems patient enough to wait a little longer for the answers, and we, here, in this brief, curious, technologically capable moment of human history, have the extraordinary privilege of being the ones who see the gap, who can point to the place where the map ends and say, clearly and with confidence, something is here that we have not yet drawn. That is not a small thing. Let us take some comfort and perspective from the history of cosmological revolutions, the moments in the past when the prevailing model of the universe was found to be incomplete, and when a deeper understanding emerged from that incompleteness. In 1543, Copernicus proposed that the Earth moves around the Sun rather than the reverse. The prevailing model of the cosmos, Earth at the centre, everything revolving around it, was not wrong in the sense of being useless. It made tolerable predictions for the positions of planets over short periods, but it was incomplete. The heliocentric model, refined by Kepler's elliptical orbits and given mathematical foundation by Newton, was a profound extension. In 1905, Einstein's special theory of relativity showed that the Newtonian mechanics that had successfully described physical phenomena for over 2 centuries required modification at velocities approaching the speed of light. Newton was not wrong within his domain, but the domain was not the whole of physics. In 1998, the discovery that the expansion of the universe is accelerating, made by the teams of Saul Perlmutter, Brian Schmidt and Adam Rees, all of whom shared the Nobel Prize in 2011, revealed that the matter-dominated universe of earlier cosmology required a new component. Dark energy, the cosmological constant reborn, was added to the standard model to accommodate this discovery. Each of these revolutions shared a common structure. First, precision measurements revealed a discrepancy between prediction and observation. Then, the discrepancy was confirmed as real rather than systematic. Then, a theoretical extension was found that accommodated the discrepancy while preserving the successes of the previous model. The Hubble tension follows this structure faithfully. We are currently in the second phase, the confirmation phase. The discrepancy has been confirmed as real. The theoretical extension has not yet been found, but history suggests strongly that it will be. The universe is approximately 13.8 billion years old. In that time, It has expanded from a state of extraordinary heat and density into the vast, structured, dark energy-permeated cosmos we observe today. It has assembled hydrogen and helium into stars. It has built in those stars every element heavier than helium. It has scattered those elements in stellar explosions across interstellar space, where they became the raw material for new stars, for planets, for chemistry, for life. On at least one of those planets, and perhaps on many more, something arose that could look back at the process, that could gather the light of distant galaxies with mirrors made from the same atoms those galaxies dispersed, that could spread that light into its component wavelengths and read, in the pattern of absorption lines, the chemistry and distance and velocity of objects billions of light years away. And that something, us, here, now, has found that the universe is slightly more mysterious than our best current model suggests, that the rate at which space expands, measured from two different directions with two different methods, disagrees in a way that demands explanation, that the first galaxies formed more quickly than our models predicted, that the cosmos, examined with sufficient precision, contains discrepancies that point toward physics we have not yet written down. This is not a source of alarm. It is a source of genuine wonder. The James Webb Space Telescope, hanging in space 1.5 million kilometers from Earth, its golden mirror cooled to near absolute zero, its instruments gathering the oldest light in the observable universe, has not shattered Einstein. It has done something more interesting, and more honest, and more valuable. It has found the edge of the map, right at the edge of what our best current model can accommodate, right at the boundary between the known and the unknown. Webb's data sits and points, not with alarm, not with certainty about what lies beyond, but with the patient, precise, statistically robust insistence that something is there, something our current map does not show, something that the next generation of cosmologists will need to draw. The history of science tells us what happens next. The discrepancy will be studied, independent methods will be applied, theoretical proposals will be tested against all available data. Gradually, through the collective effort of thousands of careful minds working across years and decades, a picture will emerge, an extension, a deeper description, a new chapter in the book that nature has been writing since the first moment. We will not live to read the full chapter. Perhaps not the next generation, perhaps not the one after. Cosmological revolutions unfold on timescales that exceed careers. But we are the generation that found the gap, that confirmed the tension was real, that built the instrument sensitive enough to rule out the systematic explanations, that pointed clearly at the place where the model ends and the mystery begins. That is not a small inheritance to pass forward. Thank you for journeying with us tonight to the edge of the known cosmos, to the place where our best models meet their limits and the universe quietly, patiently, insists on being larger than our current description, for sitting with the uncertainty and the wonder in equal measure, for finding in the incompleteness of our knowledge not disappointment, but the most honest and beautiful invitation the universe can offer. The expansion continues, the light from ancient galaxies keeps travelling, and the golden mirror keeps watching.